There's a problem hiding underneath the AI boom, and it has nothing to do with whether ChatGPT is smarter than Gemini. It has nothing to do with which company has the best model. And eventually, it may not even have much to do with who has the best chip. Because every artificial intelligence company in the world eventually runs into the exact same physical limitation: electricity. You can invent the smartest AI model anyone has ever seen. You can buy the best GPUs NVIDIA can manufacture. You can raise $100 billion, but eventually you have to plug the thing into the wall. And that sounds almost stupidly obvious until you start looking at the scale. One GPU becomes a server. Servers become racks. Racks become data centers. Data centers become hundreds of megawatts of electrical demand. And suddenly, we're not talking about software anymore. We're talking about power plants, transmission lines, natural gas, solar farms, batteries, nuclear plants, and entire electrical grids trying to figure out how they're supposed to power an industry that is growing faster than the infrastructure underneath it. So today, I want to do something really simple. We're going to start with one AI chip and follow the electricity backward, all the way from the GPU to the server, to the rack, to the data center, to the transmission system, to the power plant. Because once you see the entire chain, you start to realize something, that the AI race may eventually become an energy race. Let's start with the thing that everybody talks about, the GPU. If you followed artificial intelligence at all, you've probably heard some version of this story. NVIDIA makes the chips. AI companies desperately want the chips. The chips are incredibly expensive, and whoever gets the most chips can buy the biggest AI systems. Well, that's obviously simplified, but it's basically the public version of the AI arms race. The problem is we usually stop the story right there. We talk about the chip as though the chip somehow creates intelligence by itself. It does not. The chip needs electricity, and modern AI chips use a lot of it. A current high-end NVIDIA Blackwell GPU can operate at power levels measured in more than a kilowatt per GPU in certain configurations. Now, multiply that, because nobody building a serious AI system buys one. They combine dozens of GPUs into a server system, then dozens of those systems into racks. NVIDIA's GB200 NVL72 system, for example, combines 72 Blackwell GPUs in a rack-scale architecture. NVIDIA documentation puts a full load GB200 NVL72 rack at roughly 120 kilowatts of power. One rack, about 120 kilowatts. This is before we even start talking about a building full of them. So already the scale has changed. We're no longer asking, how much power does a computer use? No, we're asking, how much power does an industrial computing system use? And that's a very different question. Now, put those GPUs into servers. The GPU is doing the math, but it can't operate by itself. You've got CPUs, memory, storage, networking, power supplies, all of the equipment required to move enormous amounts of data between processes. Because training an AI model isn't just one giant computer working alone, it's thousands of processors working together. And those processors have to communicate incredibly fast. Think about it like a gigantic team trying to solve the same problem at the same time. Every member of that team needs information from the others. So now we're consuming electricity in two ways. We're using power to compute, and we're using power to move data. But electricity creates another problem: heat. Every watt you feed into this equipment eventually turns into heat. So the more powerful the server becomes, the hotter it becomes. And the hotter it becomes, the more cooling you need. Older server rooms could rely heavily on fans and air conditioning, but the latest AI systems are so dense that liquid cooling is increasingly becoming part of the design. You are literally moving liquid through the system to carry heat away from those processors. So electricity is powering the computation. Electricity is powering the networking. Electricity is helping power the cooling, and we're only at the server. So let's put hundreds of them together. Servers get stacked into racks. A rack is basically a large standardized cabinet filled with computing equipment. And historically, a data center rack might have consumed something like several kilowatts, maybe 10, maybe 20, depending on what was inside it. AI changes that dramatically. Now we're moving toward rack densities measured in 100 kilowatts and beyond. That is an extraordinary amount of power concentrated in a very small physical footprint. And I think this is where the AI electricity story becomes easier to understand. Imagine a traditional office building. Electricity is spread throughout the building. The building, you have lights, computers, air conditioning, you've got elevators, whatever. Now, imagine concentrating an enormous amount of electricity into one row of cabinets. Each cabinet contains extremely expensive computers running near full load, 24 hours a day, and all of the heat has to be removed continuously. That's what modern AI infrastructure increasingly looks like. And when you combine enough racks, you get something that looks less like an office building and more like a factory. Except instead of turning steel into cars, you're turning electricity into computation. That is one of the best ways to think about an AI data center. It's a factory. The raw material is electricity. The product is compute. Now, let's zoom out again. Take thousands of those servers, thousands of GPUs, hundreds or thousands of racks, put them inside a data center. Now we're talking about serious. A major modern data center can require hundreds of megawatts, and some planned AI campuses are being discussed at even larger scales. For context, ERCOT considers a site using more than 75 megawatts to be a large electricity user. And ERCOT notes that 75 megawatts during peak conditions is roughly enough electricity to serve 18,750 homes. So imagine a data center project requesting 500 megawatts. That's not a warehouse with computers in it. From the perspective of the power grid, that is basically a small city appearing on the map. Except here's the weird part. Cities grow gradually. You build houses, you build apartments, then you build businesses. Demand increases over decades. A giant data center can show up and say, we want hundreds of megawatts and we would like it in a few years. That's an entirely different planning problem. And this is happening all over the country. The Department of Energy says data centers consumed roughly 4.4% of all U.S. electricity in 2023. By 28, DOE estimates that could rise to somewhere between approximately 6.7 and 12%. DOE says total data center electricity demand could double or even triple by 28. That is a staggering shift. Not over 50 years, over a handful of years, which brings us to the next problem. Because building the data center is only half the battle. You still have to get electricity to it. This is the part nobody puts in an AI keynote. Transformers, substations. The data center can't just plug into the same electrical line that serves the gas station down the street. At this scale, you need major electrical infrastructure. The facility connects to a substation. The substation changes voltage levels and manages the flow of power. And depending on the project, that may require entirely new equipment. Now, we're dealing with enormous transformers, high voltage equipment, protection systems, transmission connections, and specialized hardware that doesn't necessarily come off a shelf tomorrow morning. This is where the difference between the digital economy and the physical economy becomes painfully obvious. A software company can scale a service incredibly quickly. You can release an update tonight. You can deploy software across the world in hours. You cannot manufacture and install a giant electrical transformer in a few hours. You cannot build a substation overnight. You can't casually relocate a high voltage transmission corridor. AI companies operate at software speed. The electric grid operates at infrastructure speed. And those two clocks are beginning to collide. Now, let's zoom out again. A substation needs electricity. Where does that come from? Well, it comes from the transmission grid. These are giant high voltage power lines you see crossing the countryside. Their job is to move huge quantities of electricity from places where it is generated to places where it is needed. And here's something really important. Having enough electricity somewhere is not the same thing as having enough electricity here. So let's say there's plenty of generation available hundreds of miles away. Well, great. Can the transmission system move it to the data center? Are those lines already heavily loaded? Is there enough capacity at the local substation? Does a new transmission line need to be built? And if so, where's it go? Who owns the land? How long does approval take? Who pays for it? Now imagine you're the grid operator and 10 different data centers all want to connect in the same general area. You can't study them fast, study them as though none of the others existed, because every new project changes the electrical conditions for every other project. This has become such a big problem in Texas that ERCOT has redesigned the way it evaluates these massive new loads. As of mid-26, ERCOT said it was tracking more than 438,000 megawatts of proposed large land connections. Nearly 90% of that proposed demand was associated with data centers. Now, here's a massive disclaimer. That does not mean 438 gigawatts of data centers are definitely getting built. They aren't. Some are speculative. Some won't get financing. Some represent competing sites. Some will just simply disappear. But ERCOT still has to evaluate what is real and what the grid can actually support, because the scale is extraordinary. ERCOT's historical peak demand record is only about 85,500 megawatts. So the raw queue of proposed large loads is several times the peak demand of the entire ERCOT system. Again, not all of this gets built, but even a fraction of it represents a massive transformation of electricity demand. And this is why Texas is such a fascinating place to watch. Texas has almost everything the AI industry wants. We've got land, major population centers, fiber infrastructure. We've got natural gas, we've got wind, we've got solar, we have battery storage, a large existing electrical grid, and political and economic environment that has historically welcomed large industrial projects. So data center developers they're showing up, and the grid basically has to ask, okay, which ones are real? Where exactly are they going? When do they need electricity, and how much? And can we deliver it? ERCOT has become so overwhelmed by the large load requests that it has moved to a batch interconnection process. Instead of evaluating gigantic projects one at a time, ERCOT studies groups of them together. That allows the grid operator to look at the combined impact of multiple proposed facilities and determine how much demand the transmission system can safely support. A project could receive everything it requested, or it could receive only part of the electricity it requested, or it just may have to wait. ERCOT began implementing its first batch zero processes in 26, specifically because the old system was no longer adequate for the scale of demand showing up. Think about what that means, though. The AI company may have the money, it may have the land, it may have the chips, it may have the building, and the power grid can still say, you can't have all the electricity yet. That is a huge bottleneck. So where does the electricity actually come from? Well, power plants, and that's usually where the debate becomes political. People want one simple answer: solar, natural gas, nuclear, wind, batteries. But the engineering problem is much messier than that. AI data centers want electricity all the time, not just when the sun's shining, not just when the wind is blowing, 24 hours a day. The EIA's current modeling treats data center server demand as essentially flat across the hours of the day. In other words, these servers are assumed to want roughly consistent electricity throughout the day. And that part matters. Solar is extremely useful. Texas has been building enormous amounts of it. During the middle of the day, solar can produce huge quantities of electricity. But at sunset, solar production disappears. Batteries can shift some of that electricity into the evening. Wind produces substantial electricity in Texas, but wind output, well, it varies. Natural gas plants can generate when they're dispatched. Nuclear provides steady output. Potential future sources like advanced geothermal and new nuclear designs are being discussed partially because of this exact challenge. DOE's own recommendations around growing data center demand includes generation, storage, transmission, expansion, grid enhancing technology, and flexible data center demand. So the solution isn't just build solar, and it isn't just build gas. The actual answer is much less satisfying. You need a system: generation, transmission, storage, flexible demand, and enough redundancy that everything still works when something breaks. This is probably the most important concept in this whole video. The electric grid isn't designed around the average day. It has to survive the difficult day, the 105-degree Texas afternoon, the unexpected power plant outage, the transmission line that goes down, the windstorm, the evening when solar output collapses but everybody's air conditioner is still running. That is the standard: reliability. Because if you're building an AI data center, You don't want electricity 97% of the time. You want it basically all the time. And if you're the grid operator, you also have millions of other customers who expect exactly the same thing. You have homes, you have hospitals, businesses, factories, schools, everything. So the question isn't simply, can Texas generate enough electricity for AI? It's, can Texas generate and deliver enough electricity for AI while still reliably serving everybody else during the hardest hours of the year? It's so much harder. Now, there is one interesting twist. Data centers might not have to behave like completely inflexible loads. So AI computing can potentially move. Maybe not your real-time ChatGPT request. If you ask a question, you want the answer now. But other jobs might be more flexible. Training, batch processing, certain background workloads. Maybe some of that computation could shift by an hour, maybe several hours. Maybe it could move from one data center to another. Maybe a company could reduce consumption during an emergency. Maybe on-site generation of batteries could temporarily supply part of the load. ERCOT is already developing connection pathways that allow some large customers to consume more electricity when transmission capacity is available, and then reduce their consumption when local grid connections become constrained. That could become incredibly important because traditionally we think of the electric grid kind of like this. Supply follows demand. People use electricity. Power plants produce enough to meet it. But AI creates an interesting possibility. Maybe certain types of computing demand can start following supply. When electricity is abundant, compute more. When the grid is stressed, compute less. If that becomes possible at large scale, AI data centers could actually become a flexible part of the electrical system, not just a giant burden sitting on top of it. And that brings us all the way back to the chip, because this is the chain. You want artificial intelligence, so you need computation. To get computation, you need GPUs. Those GPUs go into servers. The servers go into racks. The racks go into data centers. The data center connects to a substation. The substation connects to transmission. The transmission system then connects to the generation. And generation requires actual physical infrastructure. So steel, concrete, copper, turbines, solar panels, gas pipelines, batteries, transformers, transmission towers, land, workers, permits. That little AI box on your phone, that's sitting at the very end of an enormous physical machine. And that's what makes this moment so interesting. The first phase of the AI boom was mostly about software. Who has the smartest model? Who has the best chip? Who can raise the most money? But the next phase may be very, very different, because eventually everybody can order another server. Not everybody can order another gigawatt. And that's why electricity may become one of the defining constraints of artificial intelligence. Not because America is going to run out of electricity tomorrow, and not because AI is somehow impossible, but because adding electrical infrastructure at this scale, it takes time. The AI industry is growing incredibly fast. The electric grid is very big, very complicated, and very physical. And those two things, well, they're now running directly into each other. So maybe the most important question in artificial intelligence is not how smart can these models get? Maybe it's how much intelligence can we physically power? Because every AI system eventually ends up in the same place. Not in the cloud, not in some imaginary digital universe, because at the end of the chain, the cloud plugs into the wall. I'm Mike Hamilton. I'll see you in the next one.